Okay, people, let's get into second order reactions. And in this learning goal, we're going to consider two different types of second order reactions. One in which I have just only one reactant and it's second order in that reactant. And another in which it's an A plus B and it's a first order in one reactant and first order in the other reactant. So in this first one, we're going to consider the following reaction. A plus A goes to products, or I'll write that as 2A goes to B. And you can see I've got a Mathematica model down there to supplement this talk. So now if I was writing the rate of this reaction, I would write it as the following. And for now, we're not going to worry about the stoichiometric coefficient of 2 right there. When we get into more detailed work with mechanisms, we'll see when we need to apply that. So for now, I'm just going to say negative dA by dt equals K all times A squared. And now we're going to follow our same game here, where we're going to separate the two quantities in question and integrate the appropriate sides. So doing that, we end up with the following. So we'll have dA over A squared, and that equals negative kdt, sorry about that. And we'll integrate this from sum initial to sum final, and we'll integrate this from sum initial to sum final. And when we do that, we end up with the following. So the result of this integral goes 1 over the concentration of A at any time minus 1 over A initial equals KT. So we had the negative sign over there, and just doing some algebraic rearrangement, we end up with the following. And under further algebraic rearrangement, this goes as 1 over A equals positive KT plus 1 over A initial. So if we were to graph a plot of 1 over concentration versus time, we would end up with a straight line, right? So let's flush that out. Y equals mx plus b, where we can see now the slope of that line is positive, and it is the rate constant. So that's 1 over concentration, right? Well, what if we were to just plot concentration versus time? Well, it has that same property, being 1 over concentration versus time. So it looks like it's this exponential decay, but it's not. It's a 1 over x function, or I guess 1 over y in this case. So when we look at how that rate constant changes in this manipulate model here, you can see as I increase the value of the rate constant, it looks very much like what's happening with the first order reaction, where we can see the reaction is over with in a very short period of time. Similarly, I can decrease the rate constant, and that has the same effect. But again, it's important to note here that this is not an exponential decay. It's this 1 over concentration type behavior, all right? So if I now look at a plot of 1 over concentration, which is what I have here, and now this is only looking at the reactant, you can see when I scale the rate constant, right, I'm making the rate constant bigger because it's 1 over concentration. It does look like it's growing, but remember, a large K would indicate the reaction is over with over a quick period of time. Whereas a small rate constant, right, shows that the reaction takes much longer to complete. Again, because that's 1 over concentration, okay? So now continuing along, let's look at our time constants and our appropriate units, okay? So with this only being second order in one reactant, right, we came up with the following. So that goes 1 over A equals KT plus 1 over A initial. And there's several ways that we can get to the right unit with this thing. So for example, if my unit here is in seconds, let's suppose, and we note here that 1 over concentration is going to have units of liter over moles, then we recognize my K is going to have to contain this liter per mole unit, okay? So as it turns out, I'm scanning here to make sure I'm telling you right, if our rate constant then is in that reverse unit, it's going to have to be liter over mole times seconds. So liter per mole per second is the correct rate constant for a second order reaction. Because then, right, when I multiply that by seconds, I've got liter over mole equals liter over mole. Okay, so now what about our half-life? Okay, well, once again, to establish that, we can say A at any time equals 1/2 A initial. And now I can plug all of those in. So that goes as the following: 1 over 1/2 A initial equals K times T to the 1/2 power plus 1 over A initial. And now collecting like terms and doing some algebraic rearrangement, we end up with the following. T half-life equals 1 over K times the initial A concentration, right? And so just checking again to make sure that those units work, we note that this has to have units of time, so let's suppose seconds. We know that is units of moles over liters, so that means this has to be a liter per mole per second, which would then give us a 1 over seconds after the liter and mole per liter cancel, which just equals seconds. Fantastic. Okay. So now that was a discussion for having a second order reaction where we just have one reactant. So what if we have a second order reaction that looks something like this? A plus B goes to products, where it's first order in A and first order in B. So now in this Mathematica model, I've got that written as A plus B goes to C, and I can find that model right in here, okay? And so now when we start putting all of this together, we end up with the following. So I could write, with respect to A, I could say dA by dt negative equals K times A to the first power times B to the first power, right? Or similarly, I could say negative dB by dt equals K times A times B, all right? So either one of those are okay. However, we have to consider now, if we're using, let's say, the dB by dt, the concentration of A is not dependent on dB by dt, it's dependent on dA by dt, and vice versa, right? The concentration of B is not dependent on dA by dt, it's dependent on dB by dt. So we have to introduce a new quantity, and that new quantity will be X, which is the amount that's reacted. And we'll see why that is here shortly. So now instead of writing it with respect to either one of these rates, I'm going to write it as the following. I'm going to say dx by dt equals K. And now for the concentration of A, that's going to be the A initial minus however much has reacted. And then now for B, that's going to be the B initial minus however much has reacted. And both of these will be raised, right, to the first power because it's a second order reaction overall, right? First order in A, first order in B to give me second order overall. So now collecting like terms and going through that game, we have some integral from an initial to a final condition, and that's going to be dx over the following. So that will be the A initial minus X over the B initial minus X. And I can integrate this because A initial and B initial are both constants, and we can relate the amount that they react stoichiometrically by that quantity X. It's negative X for both A and B. And then, of course, that all equals integral from sum initial to final of KT. So now, integrating this is not impossible, but it gets a little complicated. So I'm just going to go straight to the result of that. And when we do that, we get the following integral, and then we get the following result with the following algebraic rearrangements. So it becomes the natural log of the ratio of B over B initial divided by A over A initial. Oh, and I didn't leave myself enough room. And all of that equals B initial minus A initial all times KT. So, and of course, I could write that in another way. If I took E of both sides, I would end up with the following. So if I take E of both sides, I end up with B over B initial divided by A over A initial equals E raised to the power B minus A times KT. And what I want to point out here, this is a second order reaction, but you can see that it does have this exponential dependency, which is kind of cool, right? And that makes good sense because it was first order in A and it was first order in B. Now that being said, this exponential dependency does take on a concentration dependence. So let's take a look at that. So here back to this initial model, right? If I turn my rate constant off and I put some amount of A in here and some amount of B, I want to get it so that they're both like very close, but not totally equal. So right, something like that. Ooh, let's maybe back it up just a little bit. Okay, so now when I scale up K, you can see that those do appear to take on this exponential decay. And we can also see that the product C takes on this exponential growth. So that's pretty cool. So let's keep flushing that out. So I'm going to go down to the next slide here, and I want to rewrite that expression one more time. So that was B over B naught divided by A over A naught, and that all equals E to the B minus A all times KT. So now we can play this game like, what if one of these is in large excess, right? So what if, let's say that B initial is much, much greater than A initial. What happens? And this is also going to be the subject of a whole next learning goal that we'll flush through in more detail. So now, if I look at this here, and to flush this out even further, I want to put this on a logarithmic scale. And I'm going to put this on a logarithmic scale by having both of them equal to the exact same concentration. And now when I increase the rate constant, you can see that it follows a linear line up to a certain point, but then decays from that linear line. And so what that means is it's behaving kind of like a first order over this period where it's giving me this straight line. But notice out at large reaction times, it does start to have some curvature. So it's not quite behaving like, you know, this first order only reaction or second order only reaction. It's dynamic. So, but now what if I increase one just ever so slightly above, okay, make them just ever so different, and now I increase K. All right, so you can see it's pretty similar behavior, but not quite, right? So now what if I make one in huge excess? So now this A is in really, really large excess, so to the point that you can't even see it on this graph. Now when I start decay, look at that. It's a total straight line. So it does appear B is truly behaving in this first order way. Okay. So we're going to explore that in a lot more detail in the next video, which will be on what's called pseudo first order reactions. I'll see you then.